Welcome friends, I'm so glad you're here. Whether you're drifting towards sleep unwinding after a long day, or simply looking for a quiet companion, you've found the right place. Before we begin, I'd love to know where in the world are you listening from. Perhaps you're wrapped in a blanket, sitting by a softly lit window, or resting somewhere under an open sky. Wherever you are, I hope you're warm, comfortable, and ready to wander with me into the stillness surrounding our young sun back to an age when the solar system is only beginning to take shape. If you find peace or curiosity in these gentle stories, please consider liking the video, subscribing to the channel, or sharing it with someone who might need a moment of stillness too. And to those who've already joined, a long thank you. The scene opens in a quiet pocket of a vast molecular cloud, where the sun forms slowly inside a collapsing knot of hydrogen and dust. It is a time without listeners, without memory, without motion beyond the gradual inward draw of gravity. Light barely escapes the thick cocoon around the protostar, turning the surroundings into a muted, warm darkness. The gas swirls in slow spirals, drifting as if unsure whether to fall inward or remain suspended, and the early solar nebula stretches around the infant star like a pale, rotating shroud. It is one of the quiet ironies of stellar birth that the violence of collapse feels at this scale like a long exhale rather than an explosion, and that the brightest object in our sky begins in a place where hardly any light passes through at all. Another soft irony lies in the slow pace of formation. Something that will one day define the rhythm of days on Earth assembles itself over tens of millions of years, unhurried and indifferent to what it will eventually illuminate. A third rests in the symmetry of the early cloud, so close to spherical in collapse, even though the future solar system will flatten into a disk so thin it could almost slice the darkness around it. As the protostar settles deeper into its cradle, heat begins to rise inside its core, though the outward appearance remains quiet and blurred at the edges. This stage, known to astronomy as T-Tauri infancy, is marked by erratic winds and soft flares, but from a distance everything looks serene, as though the star is merely adjusting itself like someone shifting beneath a blanket. The heat that emerges is entirely real. Hydrogen atoms collide more frequently. The inner pressure pushes back against gravity, and the first hints of a stable structure begin to take shape, even though nuclear fusion has not yet fully ignited. Around the stardust grains collide, gently sticking together with weak electrostatic forces, beginning the long and improbable path toward planets. In this early era, even the formation of a pebble takes far longer than any human sense of patience might allow, a reminder that the smallness of beginnings is one of the universe's most consistent patterns. Yet a subtle uncertainty lingers in these quiet nurseries. Stars often form not alone but in pairs or small groups. Observations of young stellar clusters show that binary formation is common, even likely, and some models suggest that the sun too could have emerged with a companion faint and distant drifting with it through the thinning cloud. Whether this companion ever existed remains unknown, suspended in the vast opacity of the early solar environment, concealed by the dust that now settles slowly into a broad rotating disk. The cloud around the sun continues to thin, scattering its last veils of gas into the surrounding void. Edges blur into starlight from neighbouring young stars, many of which already possess visible companions tugging at their motions. The sun, still soft and swollen with youth, hovers at the centre of a disk that grows clearer with each passing 1,000 years. The protostar brightens as it contracts, casting faint rays through gaps in the nebula, illuminating eddies of dust that drift in slow, looping arcs. These eddies move with a rhythm almost reminiscent of smoke rising in a still room, a gentle modern analogy that helps the imagination settle into the scale of these movements. In the distance, the broader molecular cloud shifts as other stars continue their formation processes, each following its own slow trajectory into brightness. The entire scene feels suspended, timeless, anchored in a moment that stretches far beyond any human measure. And yet even here another quiet irony persists. While the sun grows brighter at its core, the outer environment becomes dimmer as the residual dust drifts outward, leaving the young system both more open and more isolated. The first faint solar winds begin to push away leftover gas, sweeping it into interstellar space, carving narrow, silent path through the thinning nebula. This early solar wind is weak compared to what it will later become, but it already shapes the environment, clearing the region where planets will eventually emerge. In this stillness lies a softly noted scientific fact. The early solar wind is strong enough to influence dust patterns, but not yet strong enough to strip away the disk entirely, creating the delicate balance required for planet formation. Even so, uncertainties remain. The precise timing of this balance, the exact density of the early disk, and the subtle variations in dust composition all leave traces that modern science can only partially reconstruct. As the sun reaches the final stages of its early collapse, the surrounding disk becomes more defined, flattening into the broad, gentle spiral that will one day host worlds. The darkness of the molecular cloud gives way to a growing halo of starlight from beyond, and for the first time the sun's presence is hinted at rather than hidden. Its imagined twin, if it ever existed, would be equally concealed in this era, drifting just beyond the veil of dust, leaving only the faintest gravitational imprint, an imprint now lost to time. Yet the nebula continues to widen, opening a quiet window into the first moments of the solar system, spreading outward like a curtain slowly being drawn aside. Through this expanding stillness, the sun settles deeper into its new role, warming the dust around it, shaping the space that will eventually carry planets, comets, and billions of years of history. The long fade of the birth cloud begins with almost imperceptible motion, a slow loosening of the dense material that once wrapped tightly around the young sun, as if the nebula itself is taking a final quiet breath before drifting outward. The surrounding gas thins, gradually revealing faint glimmers of light from nearby newborn stars, each one still half hidden by the remnants of the giant molecular cloud that formed them. In this dim environment, the edges of the solar cradle dissolve into threads of dust that move like pale smoke, stretching across a space so cold that even light seems reluctant to hurry through it. Here one scientifically accepted fact emerges softly. Young stars disperse the clouds that formed them as radiation and winds push outward over millions of years. The sun is no exception, and its early energy carves slow, silent cavities through the haze, gradually clearing the region that will become the solar system's open domain. One lesser-known detail lies in the subtle glow of the receding material, a process known as fluorescence, where ultraviolet light from the young sun causes certain molecules in the thinning cloud to emit faint colours. These are hues too dim ever to be seen by human eyes, but they exist nonetheless, gently shimmering at the edges of the early nebula. As the cloud thins, uncertainties remain suspended in the cooling air. No one knows the precise structure of the original birth cloud, nor how unevenly it wrapped around the sun in these earlier stages. The nebula's density, shape, and variations have long since vanished, leaving only indirect traces in the distribution of distant small bodies and subtle isotopic signatures locked within meteorites. It is one of the universe's quiet habits to erase the earliest evidence of its own processes, a soft irony that lingers in every attempt to reconstruct these beginnings. Another irony rests in the pace of dispersal. a transformation that appears instantaneous when viewed over billions of years, unfolds slowly enough that the dust grains drifting outward would seem frozen in place to any imaginary observer nearby. A third lies in the contrast between the sun's growing brightness and the fading glow of the cloud around it, creating a scene where illumination increases even as the environment grows darker. The cloud continues to stretch and drift outward, sculpted by the pressure of radiation and the first steady flows of solar wind. These winds, though still weak, begin to sweep away the lingering wisps of gas, leaving behind a broad disk of dust and rock fragments that orbits calmly around the star. In this disk, collisions remain gentle at first, creating clumps that grow larger over long spans of time, each one following a slow and improbable path toward eventual planethood. The entire region resembles a quiet, sprawling workshop, where gravity guides every motion, drawing material into spirals that tighten gradually as the disk becomes more defined. The fading cloud around it provides an atmospheric veil, with light filtering through in narrow beams that drift across the disk like soft strokes of dawn. As the cloud dissolves, the background of space grows sharper. Stars that were once muted behind the dust now appear as faint, steady points, each one at a different stage of its own evolution. Some remain deeply embedded in their cocoons, while others shine brightly in newly cleared pockets of the nebula. The sun's early cluster companions, its stellar siblings, scatter slowly, as the gravitational bonds that once held them together loosen over millions of years. This scattering introduces another subtle scientific fact. Most stars drift away from their siblings within the first few 100 million years, and the Sun is no different. If a twin or close companion ever existed, its departure would have been almost silent, marked only by minor gravitational perturbations, lost in the broader movement of the cluster. This idea carries with it a gentle uncertainty. Astronomers continue to search for the Sun's long-lost siblings, combing through the Milky Way for stars with similar chemical compositions or matching orbital histories. Yet the trail remains faint, blurred by the vastness of time and the intricate motions of the galaxy. Even identifying a true sibling may be impossible, another quiet reminder of how much the early solar environment has forgotten. The cloud, now stretched thin across a widening region, reveals the full emerging shape of the protoplanetary disk. This disk rotates with the serene predictability, flattening under conservation of angular momentum, forming a structure so thin compared to its width that it resembles a ripple on an otherwise motionless pond. Within it, turbulence persists in soft eddies, gently stirring dust into regions of pressure that concentrate material. These eddies mirror the patterns seen in other young systems observed today, offering a glimpse into processes that remain observationally accessible only by comparing distant analogues. Yet another irony lingers in this stage. Although the disk appears calm, it hosts countless collisions, impacts, and rearrangements that build the foundation for planets, comets, and asteroids, all hidden beneath a facade of stillness. The clearing of the birth cloud also allows the surrounding interstellar environment to influence the solar system for the first time. The Sun's earliest winds begin to encounter the diffuse material of the galaxy, forming a primitive heliosphere that marks the boundary between the Sun's reach and the larger Milky Way. This boundary is soft-shifting and uncertain in structure, shaped by variable solar output and the density of the surrounding interstellar medium. Though the modern heliosphere is well studied, its early form remains a mystery, another veil of uncertainty draped across the Sun's first millions of years. As the final filaments of the birth cloud drift into the dark, the Sun stands revealed at last. Not yet a full main sequence star, but bright enough to illuminate the disk that surrounds it. Its early light shines through the last traces of the nebula, casting long, faint shadows from forming clumps of dust, giving the region a sense of emerging architecture. The entire scene carries the quiet atmosphere of something settling into its new shape, the surrounding darkness no longer an enclosure but an open space, waiting to be filled with orbit's worlds and the slow unfolding of cosmic time. In this widening stillness, the young sun continues to contract and brighten, drawing ever closer to the moment when nuclear fusion will stabilize its core. The fading cloud leaves behind an environment that feels both fragile and expansive, a place where each motion, each collision, each slow drift of dust participates in the long, patient construction of the solar system. And through it all, the quiet question of a possible companion remains unanswered, dissolved into the retreating haze, leaving only gentle hints and soft uncertainties that linger like the last threads of a cloud at dusk. Companions in stellar nurseries appear with a kind of quiet inevitability, forming not through intention, but through the simple arithmetic of gravity density and the way molecular clouds fragment under their own weight. In the region where the sun takes shape, this pattern repeats itself again and again. Knots of gas collapse in pairs or trios, drifting within the thinning cloud, like faint embers suspended in twilight. Most of the stars forming nearby emerge with partners locked into slow, mutual orbits, or loose gravitational dances that will last for millions or even billions of years. This environment is calm in appearance, yet alive with the soft movement of material folding inward, dividing and settling into multiple centers of gravity. One scientifically grounded fact rests gently at the center of this section. Observations of young star-forming regions show that binary and multiple systems are more common than solitary stars, suggesting that companionship is the default outcome of stellar birth. The sun's solitude, therefore, stands out not as an anomaly to be dramatized, but as a subtle exception within the quiet statistical landscape of star formation. A lesser-known detail weaves through this region. When clouds fragment, the separations between forming stars can be surprisingly small, sometimes only a few dozen astronomical units apart, creating environments where faint stellar siblings warm each other's surrounding dust with soft, overlapping light. Whether the sun ever shared such nearness with another forming object remains unknown, a possibility that lingers like a half-forgotten echo in the structure of the early solar nebula. Yet uncertainties lie at the heart of this story. No evidence from the present solar system records whether the sun began life with a partner, nor how long such a partnership might have lasted if it ever existed. The dynamics of the sun's birth cluster would have scattered siblings over immense distances, erasing traces of early orbits long before the solar system settled into its present form. Even chemical fingerprints, often used to identify stellar siblings, become blurred by the complexity of stellar evolution, leaving open questions that remain suspended in scientific literature without resolution. A soft irony in this landscape emerges from scale. While binary formation is a dominant outcome, most of these pairs drift so far apart over time that their companionship becomes little more than a gravitational whisper, unnoticed by any planets that might circle them. Another quiet irony rests in the sun's own path. Despite forming in a cluster dense with potential partners, it eventually finds itself wandering alone through the galaxy, a solitary traveller among billions. A third lies in the concept itself. The idea of a companion star becomes widely discussed only billions of years after the sun's birth, when the early evidence has already vanished, making the search feel like looking for a footprint in sand long washed away. In the fading haze of the early cloud, nearby protostars glow faintly, their light diffused through threads of dust. Some rotate in synchrony with their companions, creating small gravitational tides in their shared disks, pulling material into elongated shapes, or clearing narrow gaps through which starlight filters like soft ribbons. The entire region feels both crowded and quiet, a place where stars move slowly enough that their shifts could be mistaken for stillness. Through this environment, the sun resides in its broadening disk, shaping the material around it while being shaped by the motions of the nearby forming cluster. Although the sun appears alone within its immediate pocket of the nebula, the larger cluster remains close, its gravitational field influencing the outer edges of the solar system. Encounters between young stars, usually gentle at these early distances, can alter the trajectories of nascent comets or shift the structure of the disk's farthest regions. Such encounters introduce another scientifically grounded process. Young stellar clusters often experience internal gravitational interactions that redistribute material over time, influencing the distant outskirts of each forming system. Whether the Sun experienced such interactions is unclear, but the distant shape of the Oort cloud, still billions of years from forming, will eventually carry faint signatures of early stellar encounters. Even here, faint uncertainties persist. The early movement of stars within clusters remains difficult to reconstruct, as their original spatial arrangements dissolve quickly in galactic terms. While some models attempt to simulate the Sun's birth environment, each carries assumptions about density, star count, and cluster lifespan that cannot be fully verified. These uncertainties are not flaws but reflections of the vast temporal gulf between the present and the Sun's earliest days, a gulf through which only fragments of knowledge can travel. The Sun's disk continues to flatten and clear its boundaries, shaped not only by solar winds, but also by the passing gravitational murmurs of nearby young stars. These faint interactions offer subtle modern analogies like neighbouring ripples, meeting briefly on the surface of a still pond. Their influence is gentle yet real, altering patterns without disrupting the overall calm. In the surrounding nursery, companions continue to orbit one another, some tightening their orbits, others drifting apart as the gravitational well of the broader cluster weakens with time. The Sun, however, shows no clear sign of a lasting partner within its own disk. The distribution of angular momentum, the absence of large-scale distortions, and the stable structure of the emerging protoplanetary plane all suggest solitary formation. Yet none of these markers can entirely rule out the presence of a distant faint companion, one that may have drifted away early or remained hidden in the deeper folds of the birth cloud. A gentle irony flows through this notion. The more carefully scientists search for signs of a primordial companion, the clearer the Sun's solitude appears, even though the broader pattern of star formation implies that companionship is likely. In these final moments before the birth cloud disperses completely, the Sun settles into a luminous swelling at the centre of its disk. The surrounding stars, its siblings, shine softly from their own pockets of thinning dust, each carrying its own future, its own system, or lack thereof, its own quiet trajectory into galactic space. The cluster remains loosely bound, holding together like a fragile constellation that will soon drift apart. When it does, the Sun will begin its long solitary journey around the Milky Way, leaving behind the only environment in which it might ever have had a companion. Yet even now, as light slowly filters across the disk, and the last filaments of the cloud fall away, the possibility of an early twin remains neither confirmed nor dismissed, living instead. In the quiet margin between evidence and absence, a lingering question shaped by the way stars prefer companionship, even when the universe ultimately scatters them far apart. The elusive signature of a lost twin begins not with the star itself, but with the faint patterns astronomers search for long after the early solar nursery has dissolved into the wider galaxy. The Sun now stands in its mature form, burning with the steady fusion that will define most of its life. But the possibility of an ancient companion persists like a soft undertone beneath the brightness. Scientists look not for the star directly, but for the subtler gravitational traces that such a companion might have left behind, echoes written into the distant motions of comets or the structure of the outer solar system. This search unfolds slowly, extending over decades, each new observation adding texture to a question that remains unanswered. One scientifically grounded fact forms the core of this section. If a companion star existed in the early solar system, its gravity would have influenced the orbits of distant bodies, creating patterns in the Oort cloud that could in theory still be detected today. These patterns would not be dramatic or obvious. Instead, they would appear as slight statistical preferences in the directions from which long-period comets enter the inner solar system. It is a subtle signature, difficult to distinguish from random distribution, and even more difficult to interpret across hundreds of millions of years. A lesser-known detail enriches this landscape. Tiny perturbations in cometary orbits can persist astonishingly long when the objects travel distances measured in tens of thousands of astronomical units. Even small nudges accumulate over time, producing quieter symmetries that may never be fully traced to their origins. Whether these asymmetries are remnants of early gravitational interactions or merely the result of passing stars and galactic tides remains uncertain. This uncertainty is one of the soft mysteries in the study of the Sun's potential twin. Records of the solar system's earliest architecture exist only in fragments preserved in icy bodies that spend most of their lives in deep cold far beyond the reach of planetary influence. Astronomers search through distributions of orbital inclinations and aphelion directions, comparing them to models that simulate how a companion star would have shaped the far outer solar regions. These models, though grounded in physics, rely on assumptions about the Oort cloud's original mass density and formation timescale parameters that themselves remain only partially known. Here the first quiet irony emerges. The absence of evidence can resemble evidence of absence, but only when the system being studied no longer preserves its earliest patterns. Another gentle irony lies in the very nature of gravitational traces. The faintest signs of a companion are most easily erased by galactic tides, making the long-term signature of such a star vanishingly delicate. A third appears in the way scientific interest peaks long after the phenomenon in question would have mattered to planetary formation, highlighting how much later civilizations contemplate the origins of processes that resolved themselves billions of years before. The search for Nemesis, the hypothetical dark companion proposed in the late 20th century, illustrates these challenges. The idea begins from geological periodicity studies, not from direct astronomical evidence, and proposes that a distant companion might perturb the Oort cloud on regular intervals, sending waves of comets toward the inner solar system. Though elegant in concept, the hypothesis becomes more difficult to maintain as observational limits tighten. Large sky surveys reveal no stellar companion within predicted distances. Infrared observations detect no faint object consistent with the proposed parameters, and the statistical basis for periodic extinctions becomes less stable as paleontological data improves. Yet despite the fading of the Nemesis hypothesis, the broader question of whether the Sun once had a companion remains open, shaped not by extinction cycles, but by the high likelihood that stars form in pairs. The space around the Sun carries no clear gravitational signature of a present companion, and the stable orbits of planets offer no hint of recent stellar influence. The solar system's inner region is remarkably orderly, its orbital resonances shaped mainly by planetary interactions rather than external perturbations. If a twin once existed, it must have drifted far away, early wandering into the galaxy, long before planets finished assembling. The search thus moves outward to the edges of the solar system where comets rest in near-timeless suspension. Their distant realm is shaped by interactions with passing stars, molecular clouds, and the slow tidal field of the Milky Way, all of which create patterns easily mistaken for the influence of a long-lost companion. This environment introduces another scientifically grounded process. Galactic tides, though weak, can alter the orbits of distant comets, nudging them inward or outward in cycles that stretch across hundreds of millions of years. Any signature left by an early companion would be mixed with these influences, making separation nearly impossible. Uncertainties therefore multiply, not through error, but through the natural erosion of evidence across astronomical timescales. Observations continue nonetheless. Infrared surveys sweep across the sky, mapping brown dwarfs, faint red stars, and rogue planetary mass objects. The nearby galactic region becomes increasingly well charted, filling with catalogued neighbours once too dim to detect. None fit the profile of a former solar companion, yet the growing inventory deepens understanding of what the Sun's neighbourhood truly contains. A gentle modern analogy arises here. The search resembles looking for a missing book in a library that continually expands, knowing the book may never have belonged to that shelf at all. Within this process, another soft irony emerges. The more thoroughly the sky is surveyed, the more clearly the Sun appears to have no present companion, even though the statistics of star formation strongly suggest that it once might have. The gravitational history of the solar system offers a quiet landscape in which signs of a lost twin would be subtle, dispersed, and fragile. And so the search becomes less a pursuit of confirmation and more an exploration of patterns that might reveal traces of the solar system's earliest moments. As this exploration unfolds, the absence of clear evidence leaves room for unresolved questions, not as speculative drama, but as the natural outcome of studying a system shaped by billions of years of slow cumulative change. The Sun continues its solitary path through the galaxy, carrying with it only the faintest hints of its origins, while astronomers continue their careful work, tracing gravitational threads that stretch far beyond the planets into regions where certainty fades into the quiet shape of possibility. Comets as ancient messengers drift through the distant reaches of the solar system with a slowness that nearly erases the concept of motion, suspended in the deep cold far beyond the orbits of the planets. Here in the quiet halo known as the Oort cloud, countless fragments of ice and rock rest in orbits so elongated that a single journey around the Sun can take millions of years. This region, though invisible to direct observation, represents one of the solar system's most remote archives, a place where early materials remain largely unchanged since the Sun's formation. A scientifically grounded fact gently anchors this section. The Oort cloud is believed to contain material ejected from the inner solar system during its formation, mixed with fragments captured from other stars in the Sun's birth cluster. These icy bodies carry chemical signatures older than Earth itself, preserving records of conditions in a time when the Sun was still adjusting to its first light. Within them, complex molecules, crystalline structures, and primordial isotopes drift in a darkness so complete that even the faint glow of the Milky Way offers no warmth. A lesser-known detail adds texture to this stillness. Some comets contain dust grains that formed around other stars long before the Sun existed, tiny specks of interstellar wanderers gathered into the solar system during its earliest gravitational shaping. These grains, older than the planets, remain locked within icy matrices that protect them from energetic radiation, making them among the oldest surviving solid materials within reach of scientific study. This interstellar inheritance reveals the fluid boundaries of star formation, where materials migrate among systems in ways too slow to witness, but significant enough to influence the chemistry of future worlds. Yet uncertainties linger in the distant dark. No one knows the true extent or mass of the Oort cloud, nor the precise mixture of materials it contains. Estimates vary widely because the cloud lies too far for telescopes to see directly, and its existence is inferred only through the rare comets that fall inward. These comets serve as messengers from a realm that remains mostly beyond reach, offering brief glimpses of an environment otherwise lost to observation. A soft irony unfolds here. The most distant members of the solar system reveal themselves only when they leave their native region behind, warming as they approach the sun and shedding material that scientists can study only because these wanderers relinquish part of themselves. Another gentle irony lies in their trajectories, which often bring them into the inner solar system on paths so unpredictable that predicting their arrival requires both careful mathematics and a willingness to embrace uncertainty. A third rests in their apparent fragility. Objects that have endured for billions of years can disintegrate within a single pass near the sun, releasing ancient material into a domain where it will soon be lost. Comets begin their inward journeys not through sudden decisions, but through the cumulative effects of galactic tides passing stars or shifting gravitational influences at the solar system's edge. These nudges, subtle and diffuse, alter the trajectories of distant bodies in ways that unfold over vast spans of time. A passing star moving across the sun's distant neighborhood can alter the orbits of thousands of comets without ever approaching close enough to be noticed from the inner solar system. Such encounters are neither rare nor dramatic. They are part of the quiet background of galactic motion shaping the outer solar system in patterns that remain partly unpredictable. These motions introduce another scientifically grounded process. The gravitational field of the Milky Way itself exerts a gentle but persistent influence on the Oort cloud, lifting and lowering cometary orbits in slow cycles that resemble long, steady breaths on a timescale far beyond human comprehension. In the darkness of the outer cloud, comets spend the vast majority of their existence in cold equilibrium. Temperatures remain only a few degrees above absolute zero, and their surfaces accumulate microscopic scars from cosmic rays that pass through them with little resistance. These scars record time in a way planets cannot, offering a frozen chronology of energetic particles that have drifted through the galaxy for eons. Yet even these traces carry uncertainties because the exposure history of an individual comet becomes complex when its orbit shifts, sending it alternately deeper into the cloud or closer to the sun. The quiet irony of this arrangement is that these fragments, though formed in the earlier solar system, rarely reflect conditions near the sun, instead telling a story shaped primarily by their residence in a realm so distant it defies ordinary intuition. When a comet eventually begins its long descent toward the inner solar system, its journey becomes an unfolding narrative written in physics rather than intention. The object warms, gradually releasing faint jets of gas that alter its trajectory in small but measurable ways. These jets introduce uncertainties into orbital predictions not through randomness, but through the delicate interplay of sublimation rotation and internal structure. As the comet approaches the planetary region, astronomers study its path, hoping to trace backward to the region from which it emerged. Such reconstructions, while valuable, rarely lead to simple conclusions. The sun's gravitational hold weakens at great distances, and the subtle forces that shape these distant trajectories accumulate in ways that blur precise origins. The search for signs of a long-lost solar companion passes quietly through this domain. If a distant twin once existed, its influence might be reflected in patterns among the most distant comets, clustering of aphelion directions, alignments of orbital inclinations, or repeated perturbations at specific intervals. But the Oort cloud's history is layered with countless influences: galactic tides, passing stars, giant molecular clouds drifting through the galaxy's spiral arms. Disentangling these influences becomes a task defined more by patient statistical analysis than by clear causal links. The absence of strong patterns leaves room for possibilities without confirming them. In this, the Oort cloud becomes both a repository of ancient material and a landscape of interpretive quiet. Comets that fall inward illuminate the sky briefly before returning to darkness, while those that never leave their distant homes remain unseen and unmeasured. The solar system's earliest history lies frozen within these bodies, yet the same isolation that preserves them also conceals them from view. Their motions, shaped by gravitational currents nearly impossible to reconstruct, fully offer hints but not answers. This delicate balance between evidence and obscurity forms one of the soft mysteries of cosmology. The outer solar system remembers more than it reveals. As the Sun continues its orbit around the Milky Way, it carries the Oort cloud with it, like a faint halo of ancient debris shaped by forces that operate far beyond the planets. Comets remain the only messengers from this region, brief visitors whose luminous displays offer glimpses of a world that otherwise remains sealed in deep time quiet. And while their paths may someday hint at whether the Sun once shared its early cradle with a companion, for now they serve simply as reminders of the solar system's vastness, its layered history, and the gentle lingering uncertainty that accompanies the search for a star that may have vanished before Earth ever formed. The puzzling clues in long-period orbits begin with patterns so faint they almost vanish into statistical noise, emerging only when astronomers trace the paths of comets that take millions of years to complete a single journey around the Sun. These comets, arriving from the remote edge of the solar system, follow elongated trajectories that stretch deep into the Oort cloud, before swinging inward, briefly illuminating their ancient material before returning to the cold. When their orbits are mapped together, slight concentrations sometimes appear clusters of aphelion directions, or alignments of orbital inclinations inviting careful study, even though the patterns remain subtle enough to blur under closer inspection. A scientifically grounded fact anchors this section. Long-period comets do not arrive uniformly from all directions, in part because the Oort cloud itself is shaped by galactic tides and by the uneven influences of passing stars. These gravitational forces lift and tilt distant orbits over millions of years, creating natural asymmetries that can resemble the traces of a distant perturber even when none exists. This makes interpreting such patterns extraordinarily delicate, and each new dataset requires re-evaluation in light of models that simulate these long-term influences. A lesser-known detail deepens this landscape. Early analyses in the late 20th century identified apparent clustering in the aphelia of long-period comets, which inspired the hypothesis of a distant companion star. However, as survey completeness improved and more comets were discovered earlier, patterns weakened, suggesting that observational bias played a far larger role than first recognized. The sky, when sampled unevenly, produces illusions of structure clusters that seem meaningful, but dissolve as data grows. This quiet tendency of early datasets to hint at order where randomness prevails is one of the soft challenges of studying the outer solar system, especially since comets arrive irregularly and unpredictably. Yet uncertainties remain shaped not by speculation, but by the inherent difficulty of reconstructing orbits that span millions of years. Even slight perturbations from passing stars' galactic tides or internal forces within the comet itself can shift trajectories enough to complicate backward modelling. No analysis, however precise, can fully recover a comet's orbit across its entire period, especially when the gravitational environment at the solar system's edge is constantly changing. These uncertainties create a landscape where answers emerge slowly, with confidence rising only as decades of observations accumulate. Another quiet mystery lies in the distribution of cometary inclinations. Some models predict that if a distant companion once influenced the Oort cloud, the orbits of long-period comets might still show shaping forces that differ from the patterns produced by galactic tides alone. But distinguishing between these influences requires data sets far larger than what has yet been gathered, and even then the overlapping effects make clear interpretation challenging. In this complexity, the first soft irony appears: the very motions that could reveal a lost companion are precisely the motions most easily reshaped by other forces, leaving little behind for astronomers to interpret with certainty. Another gentle irony lies in the temporal scale of these orbits. Comets that return every few million years do so under conditions that have changed dramatically since their last perihelion, meaning the environment that shaped one part of their journey no longer exists when they next arrive. A third irony rests in the way modern instruments designed to reveal unprecedented accuracy simultaneously highlight the randomness inherent in gravitationally chaotic systems, reminding researchers that not all apparent patterns carry meaningful origins. The search for clues continues not through individual comets, but through large-scale statistical surveys. By comparing thousands of cometary orbits, scientists seek correlations that might hint at past gravitational events. These correlations, however, are fragile. Each new discovery reshapes the dataset, smoothing some patterns and strengthening others, yet no configuration has emerged that unmistakably signals the influence of a companion star. Instead, the patterns remain subtle, often dissolving when methods improve, or when models incorporate additional forces such as galactic plane oscillations or irregular stellar encounters. In this environment, the role of passing stars becomes particularly important. The Sun drifts through the Milky Way in a slow orbit that brings it near other stars approximately every few 100,000 years. These encounters, though distant, exert detectable gravitational influences on the outermost comets, occasionally sending some inward while altering the orbits of others that remain in the cloud. The cumulative effect of these encounters can mimic the gravitational signature of a companion, creating clusters of cometary origins that appear meaningful yet arise from external influences rather than an internal object. Such interactions underscore another scientifically grounded process. The Oort cloud is not a static structure, but a dynamic reservoir continually reshaped by forces beyond the solar system itself. The shape of this reservoir influences the paths of long-period comets, producing patterns that reflect a mixture of ancient history and ongoing galactic processes. Because of this, interpreting the structure of the cloud becomes an exercise in disentangling transient effects from long-term architecture, a task complicated by the fact that comets observed today represent only a tiny fraction of the entire population. A gentle modern analogy helps capture this challenge. Studying comet orbits is like trying to reconstruct the shape of a vast invisible forest from the positions of a few drifting leaves. Some leaves carry information about the structure of the forest, but others reflect only the breeze that carried them away. The forest remains real yet invisible, and the leaves offer fleeting partial clues. As the data set of cometary orbits expands with time, astronomers refine their models of the outer solar system, balancing gravitational theory with observational reality. Some simulations show that under certain conditions, a distant companion could have shaped specific orbital patterns, but these signatures weaken quickly as galactic tides act over time. Other simulations replicate similar patterns without requiring any companion at all. These overlapping possibilities form a landscape where evidence points in several directions at once, none of which definitively support or reject the concept of a lost twin. In this ambiguity, the idea of Nemesis remains suspended. It is neither confirmed nor fully excluded, residing instead at the boundary where data fades and models diverge. The Sun's solitary nature appears increasingly consistent with observations, yet the early likelihood of binary formation lingers as a counterweight to its apparent isolation. The quiet coexistence of these two realities, one statistical, one empirical, forms one of the soft ironies of stellar origin studies. What is likely at birth does not always persist into maturity. As this section draws into stillness, the distant comets continue their slow drift, unaffected by human curiosity, shaped only by the ancient ongoing forces that govern the outer solar system. Their orbits remain long, their rhythms nearly silent, their patterns elusive yet essential to any attempt to understand how the Sun's surrounding halo formed and evolved. Whether they hold faint clues to a lost companion, or simply record the cumulative influence of the galaxy itself, they persist as the quiet messengers of a realm that remembers more than it reveals, offering glimpses of history so faint that even the brightest instruments struggle to draw them into clarity. The deep cold of the Oort cloud settles around the solar system like a nearly perfect silence extending outward for distances so vast that even the concept of boundary becomes a soft approximation rather than a defined edge. Here, more than a light year from the Sun, the faint glow that warms the inner planets fades into a darkness where temperature hovers only a few degrees above absolute zero. Comets rest in this expanse the way dust motes rest in still air, each one suspended in an orbit so elongated and slow that motion itself becomes almost conceptual. These icy bodies, remnants of the solar system's earliest stages, drift far beyond the planets, far beyond the heliosphere's comfort in a realm shaped more by the galaxy than by the Sun. A scientifically grounded fact anchors this landscape. The Oort cloud, though never observed directly, is supported by the behavior of long-period comets, whose trajectories require a reservoir of distant bodies scattered into near-spherical distribution around the Sun. Models suggest that during the solar system's chaotic formation, gravitational interactions with the giant planets flung countless icy fragments outward. Instead of escaping entirely, many settled into remote orbits, bound so loosely that even the passing influence of the Milky Way's tides affects their paths. In these conditions, comets carry the solar system's earliest materials into a realm where time stretches almost without friction. A lesser-known detail adds quiet texture beyond roughly halfway through the Oort cloud's estimated extent. The Sun's gravity weakens enough that comets hover on the very threshold between belonging and drifting free. In this liminal zone known as the outer cloud, a comet's allegiance to the Sun becomes delicate, a soft negotiation influenced by distant stars and the galaxy's tidal pull. This balance allows objects to remain bound for billions of years, while still susceptible to the faintest nudges, a condition that makes the cloud both stable in form and constantly reshaped at its edges. Yet uncertainties envelop this entire region. No instrument has detected the Oort cloud, directly leaving its size, mass, and precise structure inferred only from the comets that occasionally fall inward. Even the distribution of their orbits reveals only partial information, obscured by observational bias and the rarity of these long-period arrivals. Whether the cloud is sharply bounded or blends smoothly into interstellar space remains unknown. Whether the Sun's birth cluster influenced its formation more strongly than later galactic tides cannot be reconstructed in full. These uncertainties are not gaps, but reflections of a domain that lies too distant, too cold, and too faint for direct study. They illustrate the quiet fact that the universe guards its earliest architecture with layers of distance and darkness that science approaches only through careful inference. The first soft irony emerges here, the region furthest from the Sun, where gravitational loyalty is weakest, holds some of the most pristine materials from the solar system's infancy. These icy bodies preserve chemical signatures unchanged for billions of years, precisely because they reside where the Sun can barely reach them. A second irony lingers in the knowledge that the galaxy, not the Sun, acts as the primary sculptor of these distant orbits, making the farthest part of the solar system a place shaped by forces external to it. A third rests in the slow, quiet arrangement of the cloud itself. While the inner planets move swiftly and predictably, the outermost comets follow rhythms so long that a single revolution may see entire species rise and vanish on Earth. In the cold, outer darkness, each comet's orbit reflects a delicate interplay between solar gravity and galactic structure. The Milky Way's mass exerts tidal forces that cause the cloud to stretch, especially in directions perpendicular to the galactic plane. These tides alter the shapes of orbits over immense timescales, gradually raising or lowering their aphelia in cycles that unfold more slowly than any geological process on Earth. Passing stars exert additional perturbations. Most pass too far to leave noticeable signatures, yet over billions of years even distant encounters influence the cloud's architecture, redistributing objects in ways that can mimic the gravitational pull of a distant companion star. Whether such patterns record the traces of a lost twin or simply the cumulative effect of external forces remains an unresolved question. The Sun itself travels through the galaxy in an orbit that carries the entire cloud with it, a halo drifting through an environment filled with subtle gravitational contours. As the Sun moves through different regions of the Milky Way, including dense spiral arms, inter-arm spaces, and local fluctuations in stellar density, the cloud responds with motions too faint to observe directly. Small gravitational variations may tilt the orbits of outer comets or gently alter their distribution. Yet even these influences remain theoretical when applied to specific objects because the timescales involved erase traces before they can be reconstructed. A gentle modern analogy captures this challenge. The Oort cloud behaves like a vast invisible dandelion puff drifting through a slow breeze. Each filament remains attached yet trembles at the slightest disturbance, and the shape of the whole reflects the combined influences of breezes long past. Moving inward from the outermost regions, the so-called inner Oort cloud lies closer to the Sun but still beyond the reach of planetary interaction. Its comets, though more tightly bound, remain frozen in near-permanent darkness. Some models suggest that this inner cloud, sometimes called the hills, cloud contains far more mass than the outer halo. If true, its stable reservoir may provide long-period comets for billions of years to come. But this too carries uncertainties. The number of bodies, their density distribution, and their formation history remain topics of active study. Even the existence of a distinct inner cloud remains partly speculative, inferred indirectly from models designed to reconcile the observed frequency of long-period comets with the number that would be needed to maintain that frequency across geological timescales. Here another soft irony appears. The region that may contain the majority of the Oort cloud's mass is the one from which the fewest messengers emerge. Because this inner reservoir sends fewer objects inward, it remains all but invisible, even though it may hold the most complete archive of the solar system's distant past. These objects, by virtue of their stability, preserve structures that even galactic tides struggle to reshape, creating a quiet paradox in which the most informative region of the cloud is also the one least likely to ever reveal itself. The search for signs of a lost solar companion occasionally turns toward this region. In some models, a distant partner, whether a faint star or a brown dwarf, could have influenced the distribution of inner cloud objects, nudging them into more stable or more polarized configurations. Yet the absence of direct observation makes such inferences difficult. The Sun's gradual drift away from its birth cluster and its long interactions with the galaxy introduce additional variables that obscure any original signatures. Even if a twin existed, its gravitational imprint would be layered beneath billions of years of subsequent motion. Comets within the cloud do not perceive these complexities. They rest in slow equilibrium, moving through orbits so vast that their curvature is almost imperceptible. Their paths, shaped by forces older than planets themselves, remain quiet expressions of the solar system's earliest history. Occasionally one is nudged inward, beginning a journey that spans millions of years and eventually brings it into the inner solar system, where it warms, brightens and reveals material unchanged since the dawn of the sun. These rare arrivals provide glimpses into the nature of the Oort cloud, yet each carries only a fragment of the greater whole. The cloud itself remains hidden, a structure defined by absent silence and the cold persistence of objects that have outlived countless cycles of motion within the galaxy. In this distant realm, where the sun's warmth no longer guides, and where darkness reigns nearly absolute, the possibility of a long-vanished companion lingers only as a question, without urgency, shaped by the slow, steady interplay of forces that govern the outermost boundaries of the solar system. And through this quiet, the comets continue their patient drift, suspended in time so extended that even the search for a twin star becomes only one more layer of uncertainty, resting gently over an ancient and enduring cold. A hypothesis born from patterns emerges slowly, not from the bright centre of the solar system, but from the long, careful study of Earth's deep geological record, where extinctions rise and fall in rhythms subtle enough to invite interpretation, yet complex enough to resist simple explanations. In the late 20th century, paleontologists examining marine fossil diversity proposed that mass extinctions appear to follow a repeating interval roughly every few tens of millions of years, with peaks that seem too regularly spaced to be dismissed as coincidence. This idea, intriguing yet delicate, prompted astronomers to look outward, imagining whether something in the far reaches of the solar system might periodically disturb the Oort cloud, sending cascades of comets toward the inner planets. A scientifically grounded fact anchors this section. The Nemesis hypothesis grew from an attempt to link geological cycles with celestial mechanics, suggesting that a distant faint companion star could periodically perturb the Oort cloud and trigger waves of comet impacts on Earth. The mechanism itself rests on principles well understood. Stellar perturbations can indeed alter the distribution of comets, but translating periodic geological signals into astronomical requirements demands precision that the data of that era struggled to support. Still, the idea took shape, gaining attention, because it bridged disciplines rarely connected at such scales. One lesser-known detail woven into this origin is the reliance on early paleontological data sets that were limited in both completeness and resolution. Fossil records preserved unevenly across geological strata can generate apparent periodicities when sampling is incomplete, producing cycles that seem meaningful but reflect preservation patterns rather than biological or astronomical realities. These early data sets, foundational yet fragmentary, guided the interpretation towards cycles that modern analyses treat with greater caution. Even so, the hypothesis captured imagination because it proposed a cosmic agent influencing Earth's surface history, a suggestion that simultaneously honored known gravitational principles and stretched them into a new interpretive space. Uncertainties, gentle yet persistent, surround this entire narrative. The geological record, though rich, remains imperfect. Sediments erode, fossils vanish, and depositional environments vary widely over time. Parsing true biological extinctions from sampling gaps becomes an exercise in statistical inference. Similarly, the dynamics of the distant Oort cloud remain only partially understood, shaped by forces that operate on timescales longer than most geological cycles. The overlap of these uncertainties means that any proposed periodicity carries margins that make precise astronomical coordination difficult to affirm, and so the Nemesis hypothesis occupies a liminal position, suspended between geological pattern recognition and astronomical modelling, never fully embraced, yet never entirely dismissed, until observational evidence later eroded its plausibility. A soft irony appears at the heart of this episode. The search for a catastrophic cosmic explanation arose during a time when Earth's own geological processes, volcanism, plate tectonics, and climate cycles were just beginning to be understood in their full complexity. A second irony rests in the fact that the solar system, which seems so orderly in its planetary orbits, harbours regions of profound gravitational chaos, yet the evidence of their influence on Earth proves far more subtle than early interpretation suggested. A third gentle irony lingers in the way the hypothesis, though ultimately unsupported, catalysed decades of fruitful research, leading to advancements in infrared astronomy, improved surveys of nearby stellar objects, and refined models of comet dynamics, outcomes unintended by those who first proposed the star itself. As astronomers explored the implications of a distant companion, they calculated the possible orbit such a star would require. It would need to be extremely faint, perhaps a red dwarf or brown dwarf, orbiting the Sun at distances of tens of thousands of astronomical units, completing a single circuit every tens of millions of years. Such a star would interact only weakly with the planets, but could in theory exert subtle influence on the Oort cloud. Models simulated this possibility, tracing how periodic tidal interactions might introduce waves of comets into the inner solar system. But these models, though mathematically sound, rely on assumptions about the Oort cloud's mass and distribution that remain uncertain. When observational astronomy joined the conversation, it brought constraints that quietly reshaped the hypothesis. Infrared sky surveys, particularly those designed to detect faint, cool objects, began to rule out large swathes of parameter space where a companion could hide. The absence of a detectable partner diminished the likelihood of Nemesis long before the geological periodicity was reassessed. By the early 21st century, surveys such as 2MASS and WISE reduced the possible mass and distance range to levels difficult to reconcile with the original hypothesis. Yet even as the search narrowed, the underlying question shifted, not whether a star presently orbits the Sun, but whether one may have done so in the deep past, drifting away before the modern solar system settled into its current form. This transition reflects another gentle mystery in stellar evolution. Young stars often form in clusters that dissolve over time, scattering sibling stars across the galaxy. In such environments, gravitational encounters can gently separate wide binaries, especially those whose separation stretches so far that they barely remain bound. If the Sun once had a distant partner, this companion could have drifted away within the first few 100 million years. Long before the Oort cloud finished forming, long before Earth's geological rhythms began. This possibility softens the modern dismissal of Nemesis not by substantiating the original hypothesis, but by acknowledging that a companion could have existed without leaving a detectable impact on the present solar system. It highlights the boundary between what can be ruled out now and what remains unknowable about the earliest epochs. The Nemesis idea, shaped by interdisciplinary curiosity, also illuminated the difficulties of aligning geological and astronomical timescales. Earth's sedimentary layers record changes influenced by volcanic activity, sea level fluctuations, atmospheric composition, and biological evolution processes that unfold according to rhythms intrinsic to the planet. Some cycles arise from orbital variations governed by celestial mechanics, but others emerge from internal feedbacks that have nothing to do with the outer solar system. Distinguishing among these requires patience and the recognition that resemblance does not imply causation. A soft modern analogy helps frame this. Geological rhythms resemble overlapping ripples on a pond, some caused by stones thrown nearby, others by distant disturbances, and still others by the pond's own shifting edges. Passing their origins demands long observation and a willingness to recognize ambiguity as intrinsic to the system. As paleontological datasets expanded and statistical methods improved, the apparent periodicities softened, their regularity diminished by new fossil discoveries and more refined stratigraphic techniques. Extinction events became more clearly linked to Earth-bound processes such as volcanic outgassing during large igneous province eruptions or shifts in ocean circulation, triggered by climatic extremes. These explanations, grounded in geological evidence, offered simpler and more consistent interpretations than a distant star. Thus, the Nemesis hypothesis gradually receded not through sudden refutation, but through the steady accumulation of data that made alternative explanations more compelling. Yet its conceptual legacy remains. It demonstrated how questions at the boundary of disciplines can stimulate productive exploration even when their initial framing proves incomplete. In the quiet afterglow of the hypothesis, the idea of the Sun's potential twin persists in a gentler form, not as a destroyer of worlds or a cyclic disturber of the Oort cloud, but as a possibility rooted in the common formation pathways of stars. The statistical likelihood of early companionship remains high, even if no evidence confirms such a partner's identity or fate. This leaves the narrative suspended, shaped not by dramatic arcs, but by the quiet recognition that the early solar system, like the broader galaxy, contains far more history than can be fully recovered. In this slow contemplative space, the Nemesis hypothesis becomes less a failed idea and more a reflection of how science searches for patterns across vast timescales, how hypotheses rise from fragments of evidence, and how understanding grows through the gentle, steady accumulation of knowledge rather than through singular revelations. The irony of ancient catastrophes settles into view not through sudden violence, but through the slow, layered history of Earth's deep past, where mass extinctions unfold across intervals far longer than any single moment of impact or upheaval. The geological record, shaped by sediments laid down over millions of years, shows that many extinction events, those long associated with cometary catastrophes or sudden cosmic triggers, often develop through extended periods of environmental stress. Volcanic outpourings alter atmospheric chemistry, continental rearrangements disrupt ocean circulation, and climate shifts reshape ecosystems long before species disappear entirely. Against this backdrop of gradual change, the idea of a distant star periodically sending waves of comets toward Earth finds little steady anchorage. A scientifically grounded fact anchors this section. The majority of known mass extinctions correspond more closely with terrestrial processes, large igneous province eruptions, atmospheric and oceanic chemistry disruptions, and long-term climate change than with evidence for repeated comet impacts. While some extinctions do coincide with impact signatures such as the Chicxulub event, marking the end Cretaceous, these are isolated findings rather than rhythmic patterns. Even in cases where cosmic influences appear, they act as part of a broader landscape of environmental challenges, rather than as singular periodic drivers. A lesser-known detail adds depth to this understanding. Many extinction boundaries reveal subtle precursor stresses preserved in microfossil assemblages and geochemical anomalies. These signals show species declining or shifting their ranges long before the events that mark the formal boundary in the rock record. Such gradual declines stand in contrast to models proposing sudden external triggers, revealing instead ecosystems already destabilized by long-term environmental pressures. These quiet layered transitions connect more closely with processes internal to Earth than with episodic disturbances from the solar system's outskirts. Yet uncertainties remain woven into the geological archive with the same quiet persistence as the sediments themselves. Erosion removes layers, tectonic activity buries evidence, and uneven preservation biases the fossil record towards certain environments. These gaps mean that correlations between impacts and extinctions sometimes appear ambiguous, not because they contradict one another, but because the rock record is incomplete. Where cometary signatures exist, they rarely align neatly with extinction timelines. Where they do not, their absence cannot always be taken as definitive. This interplay of evidence and absence forms the quiet scientific mystery of extinction research, disentangling simultaneous influences across timescales that stretch far beyond human intuition. In this landscape of complexity, the first soft irony emerges despite the dramatic imagery. Comet impacts evoke most of the profound changes in Earth's biological history, seem driven not by sudden cosmic events, but by the slow, persistent forces of geology, forces so steady that their cumulative effects rival even the most powerful extraterrestrial collisions. A second gentle irony lies in how the Nemesis hypothesis, which imagined a celestial mechanism for repeated devastation, arose during a period when Earth's own deep processes were only beginning to be understood in full. A third rests in the recognition that even the catastrophic Chicxulub impact, often held as the quintessential sudden extinction trigger, occurred in a world already experiencing volcanic activity and shifting climate conditions that amplified its consequences. Throughout Earth's history, multiple influences intertwine to produce the major transitions that punctuate the fossil record. The Great Oxygenation Event, for example, transforms the atmosphere through the slow rise of cyanobacteria unfolding over hundreds of millions of years. The Permian extinction, the most severe loss of life in the fossil record, corresponds with massive Siberian volcanism that releases greenhouse gases over extended timescales, destabilizing climate systems in ways that require no external catalyst. Even snowball Earth episodes arise from complex interactions between tectonics weathering and atmospheric carbon dioxide, all internal to the planet's evolving systems. These events highlight the delicate balance between Earth's internal mechanisms and the broader cosmic environment. While external forces can and do influence life, the planet itself generates conditions for both flourishing and collapse. This makes the search for rhythmic, externally driven catastrophes inherently challenging, because observed extinctions seldom follow strict cycles. Instead, they arise from shifting interactions within the Earth system. Astronomers pursuing the Nemesis idea grappled with these complexities early on. If a distant companion periodically perturbed the Oort cloud, its influence on extinction patterns would require impacts large and frequent enough to leave global signatures. But the impact record lacks such regularity. Large craters scatter across geological time without forming a consistent interval, and many coincide with no known extinction event at all. Impact ejecta layers, when present, appear sporadically and often without accompanying biological turnover. These observations gently erode the foundation of a periodic cosmic causation, replacing it with a quieter understanding. Earth's surface history is shaped more by the planet's internal rhythms than by distant gravitational influences. In the outer solar system, meanwhile, comets continue their slow drift unaffected by the debates unfolding on Earth. The Oort cloud remains shaped by passing stars' galactic tides and the faint pull of the Sun. Its icy bodies do not adhere to cycles imposed by a partner star, nor do they arrive with the precision that a periodic extinction model would require. Their arrivals, often influenced by millions of years of gradual orbital evolution, resist simple synchronization. This natural irregularity introduces further uncertainty into any attempt to link impact events to an unseen celestial companion. A gentle modern analogy offers clarity: extinction patterns resemble overlapping geological tides, shaped by continent movement, global chemistry, and climate dynamics. They rise and fall, not with clock-like precision, but with the fluid complexity of interacting Earth systems. These internal tides may occasionally coincide with cosmic disturbances, but coincidence does not imply periodic causation. Over time, as paleontological datasets expand and stratigraphic techniques refine the perceived regularity of extinction, intervals weakens. Statistical reanalyses show that what once appeared cyclical becomes inconsistent under improved sampling. Larger datasets, from microfossils to terrestrial flora, reveal extinctions unfolding across varied timelines, sometimes concentrated, sometimes extended. These patterns reflect an Earth driven by internal feedbacks rather than by an external celestial metronome. Meanwhile, improvements in astronomical surveys further undermine the Nemesis concept. Infrared observations reveal no hidden star within predicted ranges. Stellar motions traced through Gaia data show no object moving consistently with the Sun across galactic space at the required distance. The absence of a companion becomes increasingly clear, and so the link between periodic extinctions and a hypothetical twin grows fainter. Yet the idea does not vanish entirely because the underlying curiosity persists. Could the Sun, like many stars, have formed alongside a partner that drifted away early? This question separates itself from extinction studies standing on its own as a plausible scenario rooted in star formation statistics rather than in geological cycles. The fading of the Nemesis hypothesis thus redirects inquiry rather than extinguishing it. The absence of periodicity in mass extinctions reveals more about Earth's internal complexity than about the solar system's architecture. The Sun's potential early companionship remains an open question, yet its role in shaping Earth's biological history diminishes with every new geological insight. In this spacious contemplative perspective, the search for cosmic causes becomes a window into the broader interplay of planetary and stellar processes. The solar system drifts through the galaxy, carrying with it the Oort cloud and its quiet ancient comets, while Earth, shaped by its own deep rhythms, experiences cycles of change that unfold in the slow language of geology. The catastrophes that punctuate its past, though momentous, arise from layers of causes that resist simple explanations. And in this gentle complexity, the idea of a dark twin star softens from a catastrophic agent into a quiet possibility belonging to a time so distant that even Earth's extinctions become only one small part of the story. Searching the infrared darkness begins with a shift in perspective, away from geological records and statistical patterns, and toward the quiet vastness of the night sky, where faint objects too cool to shine in visible light emit their energy as long, soft wavelengths that reveal themselves only to specialized instruments. If a distant companion to the Sun existed, especially one small or dim enough to have escaped early detection, it would glow primarily in the infrared hidden from ordinary telescopes, yet gently luminous, in a spectrum where heat itself becomes a form of light. This search unfolds across decades, each new survey adding clarity to a sky that once seemed filled with possibilities. A scientifically grounded fact anchors this pursuit. Cool stars, brown dwarfs, and substellar objects emit most of their radiation in the infrared, making all-sky infrared surveys the most effective way to detect potential companions. Instruments such as the 2-micron All-Sky Survey 2MASS, and later the Wide-Field Infrared Survey Explorer WISE, mapped the sky with sensitivity capable of detecting objects many thousands of times fainter than the faintest stars seen in visible light. These missions transformed the search landscape, revealing a population of cool, dim bodies scattered throughout the solar neighborhood. A lesser-known detail adds texture to this exploration. Brown dwarfs, sometimes called failed stars, come in a continuum of temperatures and masses, some glowing faintly at only a few hundred degrees above absolute zero. The coldest known objects emit primarily in mid-infrared wavelengths, invisible even to earlier infrared surveys. This means that only with the advent of more sensitive detectors did the full diversity of these objects begin to emerge, offering a clearer understanding of what the Sun's surroundings actually contain. Despite this growing catalogue, no object matching the characteristics of a distant solar companion appeared within the ranges predicted by Nemesis models. Yet here uncertainties linger, not through speculation, but through the limitations of measurement. Surveys detect brightness, but not always distance. Objects must be cross-referenced with precise astrometric data to determine whether they move alongside the Sun through the galaxy, or merely pass through the field of view at vastly different distances. Before Gaia's precision, identifying true neighbours required careful analysis, and even then the faintest objects remained ambiguous until their motions could be tracked over time. In this gap between detection and identification, the first soft irony emerges. The sky became more crowded with potential candidates, just as improved analysis ruled nearly all of them out. A second gentle irony appears in the fact that the more completely astronomers surveyed the infrared sky, the more compelling the Sun's solitude became, despite early expectations that the solar system might follow the common pattern of binary formation. A third rests in the surprising richness of the newly revealed population, hundreds of brown dwarfs nearby, none of which belong to the Sun, yet all of which reshaped understanding of how common faint companions are in general. The search refined itself with each mission. 2MASS revealed the brightest brown dwarfs mapping the closest and still warm substellar neighbours. Successive surveys deepened the reach. WISE, scanning the sky at 4 infrared wavelengths, uncovered objects cooler than previously known, including the Y dwarf class, whose temperatures overlap with those of Earth-like environments. These discoveries expanded the inventory of the dimmest stars and star-like objects, yet none shared a trajectory compatible with that of a long-bound solar companion. Astronomers traced proper motions, small shifts in position over months or years, to identify whether any dim object moved through space in tandem with the Sun. None did. The absence of such shared motion strengthened the conclusion that no companion remained gravitationally linked to the Sun at present. Still, the search carried a quiet mystery. If the Sun once had a wide separation twin, gravitational interactions within its birth cluster could have separated them early. A companion that drifted away in the first tens of millions of years would now be indistinguishable from any other star wandering in the galaxy. Its identity, if it exists at all, would be hidden among billions of unassociated stars. Infrared surveys cannot disprove an ancient separation. They can only map what remains. This introduces a gentle uncertainty. The lack of a current companion does not rule out one long vanished. Within the observable search, astronomers also considered the gravitational influence a present companion would have on the solar system. A star of sufficient mass to perturb the Oort cloud on periodic intervals would need to reside within a specific range of brightness and distance, making it potentially detectable with modern infrared capabilities. As larger and colder brown dwarfs were catalogued, models were updated, shrinking the parameter space further. Eventually, the window for a companion massive enough to influence comet distributions closed almost entirely, leaving only the possibility of extremely low-mass objects far too small to fulfill the requirements of a Nemesis-like perturber. A gentle modern analogy helps frame this narrowing. The search resembles examining a vast dim landscape with increasingly sensitive lanterns, only to find that each brighter lantern eliminates more hiding places until only non-viable corners remain. The infrared sky revealed an abundance of neighbors, small stars, brown dwarfs, free-floating planetary mass objects, each drifting quietly through space. Among these discoveries, systems like the brown dwarf pair WISE 1049 Pfeifferus Lumen 16 showed the richness of nearby substellar space, residing only a few light-years away. Such finds inspired excitement, not because they were solar companions, but because they demonstrated how much had remained unseen. And yet none followed the Sun's path through the galaxy. None matched the distances motions or expected brightness profiles of a long-lost twin. The precision of modern astrometry further refined these conclusions. Gaia's measurements of stellar motions allowed astronomers to identify co-moving stars with extraordinary accuracy. A true solar companion, regardless of its brightness, would share the Sun's general galactic motion, revealing itself through common velocity. But Gaia found no such object within realistic distances. Its absence illustrated another soft irony, the Sun forming in a cluster, where companionship was statistically likely ended up travelling through the galaxy alone, while numerous binary and multiple systems surround it in the stellar neighbourhood. At the same time, the infrared searches contributed to broader understanding of the Sun's environment. They revealed the demographics of brown dwarfs, constrained models of star formation, and improved maps of nearby space. These contributions remain valuable, even though they did not uncover a solar twin. The search for Nemesis became in practice a survey of the faintest objects in the galaxy, a study of what exists rather than of what is missing. Even now, the faintest substellar objects challenge detection, their heat signatures barely above the cosmic background. Yet the limits of observational capability continue to shrink. If a companion remains undiscovered, it must be exceptionally small and distant, incapable of exerting meaningful gravitational influence on the solar system. This renders it irrelevant to the hypothesis of periodic comet disturbances and limits its significance to the question of early solar companionship, a question that infrared data cannot fully answer, because it maps only the present. The infrared darkness, once filled with the possibility of a hidden star, now appears rich, yet empty of the specific object imagined by the Nemesis hypothesis. Instead, it reveals a tranquil stellar neighborhood where the sun shines alone, surrounded by quiet companions not bound to it, but sharing the broader galactic drift. In this stillness, the search becomes less about confirmation and more about understanding the vast, cool landscape in which the sun travels, a region where dim objects whisper their faint heat into the darkness, while leaving the question of a long-vanished twin suspended just beyond the reach of present knowledge. A sky filled with brown dwarfs unfolds not as a landscape of dramatic discovery, but as a quiet revelation of how much had once remained unseen, hidden in wavelengths, inaccessible to the human eye. As infrared surveys deepen their reach, the space within a few dozen light-years of the sun transformed from a sparse neighborhood into one populated by faint, cool bodies, objects neither fully stars nor precisely planets, occupying the liminal category of substellar objects. These brown dwarfs, glowing softly with residual heat from their formation, drift in solitude or in loose companionship with other faint partners, each one illustrating the diversity of stellar outcomes. A scientifically grounded fact anchors this section. Brown dwarfs form like stars through the collapse of molecular cloud fragments, but they lack the mass required to sustain hydrogen fusion in their cores. Without this stable energy source, they cool slowly over billions of years, emitting primarily infrared radiation that makes them nearly invisible in the optical bands. Modern surveys have revealed that these objects, once thought rare, are common in the Milky Way's local environment, adding nuance to our understanding of how fragmentation shapes young stellar nurseries. A lesser-known detail brings texture to this landscape. The coldest brown dwarfs, classified as Y dwarfs, reach temperatures not much higher than those of Earth's surface, giving them spectral signatures shaped by ammonia and other molecules rarely seen in warmer astrophysical contexts. These objects challenge observational limits, appearing only as faint pinpricks in mid-infrared data. Some drift alone, others orbit small stars at great distances, and a few form binary pairs with separations small enough that their mutual orbit resembles a slow dance in deep time, yet uncertainties linger gently across these discoveries. The true number of brown dwarfs in the solar neighborhood remains unknown, limited by instrument sensitivity and the challenge of distinguishing faint objects from background noise. Some may lie just beyond current detection thresholds, hidden, not because they are distant, but because they are exceptionally cool. Others may be detected without distance measurements, making their spatial relationship to the sun uncertain until their motion is tracked over years. These uncertainties illustrate the limits of the observational frontier, where data sharpens slowly and faint sources require patient accumulation of measurements. Within this landscape, the first soft irony emerges. Brown dwarfs prove abundant, perhaps as numerous as small stars, yet their faintness makes the sun's immediate surroundings appear deceptively empty until infrared surveys reveal their quiet presence. A second gentle irony appears in the fact that although many brown dwarfs form in binary systems, none share motion with the sun, reinforcing the conclusion that the sun travels alone while companionship flourishes all around it. A third rests in the way these objects, once considered potential hiding places for a hypothetical nemesis, instead became markers that ruled out such a star by filling the catalogue without producing a match. The discovery of nearby brown dwarfs deepened understanding of star formation in significant ways. Systems like Lumen 16, a binary brown dwarf pair only a few light-years from the Sun, illustrated how common small multiples can be, and how faint neighbours had escaped notice until infrared technology advanced. These systems also helped refine models of substellar cooling atmospheric chemistry and mass distribution near the hydrogen-burning limit. By mapping their numbers and characteristics, astronomers gained insights into the proportion of molecular clouds that fragment into low-mass objects versus full-fledged stars. This knowledge in turn refined the context in which the Sun formed. If the Sun emerged from a typical star-forming region, the presence of many low-mass companions in the galaxy suggests that early companionship was entirely plausible. But the absence of a present companion shows that such relationships can be fragile, especially for wide binaries whose gravitational bonds weaken over time. In this sense, the presence of neighbouring brown dwarfs offers indirect evidence not about what the Sun retains, but about what it might have lost. The search for the Sun's hypothetical dark twin intersects with this broadened understanding. For Nemesis to influence the Oort cloud in the manner once proposed, it would need to fit within a narrow mass range massive enough to shape long-period comet trajectories, but faint enough to evade early detection. Brown dwarfs, especially those warmer than the coldest white dwarfs, fall within that range. But the infrared surveys revealed none co-moving with the Sun. Instead, each faint neighbour moves through space along its own independent trajectory, shaped by its own origin and history. Gaia's astrometric precision confirmed this independence. Stellar motions across the sky reveal which objects share the Sun's general galactic drift, and which only pass through its vicinity. A true companion, regardless of brightness, would trace a path consistent with long-term gravitational association. But no brown dwarf or any other infrared source matches this criterion across published datasets. The absence of such motion stands as one of the strongest constraints on the existence of any present-day solar companion. Yet a gentle mystery remains. If a companion existed in the early solar system, it could have drifted away under the influence of the Sun's birth cluster before the Oort cloud fully formed. In that case, the infrared sky, no matter how thoroughly mapped, would not reveal the long-lost twin. It would instead show only the present state of the Sun's surroundings, not the distant memory of its origin. This disconnect between present observation and ancient configuration illustrates the boundary where astronomy meets deep time, the boundary beyond which evidence fades and the galaxy's motion erases past relationships. A soft modern analogy conveys this: the Sun's early companionship, if it existed, resembles a childhood friend whose path diverged before memory could record their shared beginnings. The brown dwarfs now catalogued around the Sun form a constellation of possibilities that clarify the Sun's solitude without revealing its earliest associations. The inventory of nearby brown dwarfs also reshapes understanding of the Sun's local environment, independently of the Nemesis question. These faint objects influence the dynamics of interstellar gas, contribute to the galaxy's total mass, and provide testbeds for atmospheric physics in regimes unreachable by planetary telescopes. Their presence underscores how much of the galaxy is formed not by bright stars, but by objects so faint they glow only with the residual warmth of their formation. As the search for the Sun's hypothetical companion fades into the broader exploration of the substellar population, the infrared sky becomes a repository of quiet knowledge. It contains no dark twin shaping the solar system's distant boundaries, yet reveals a richness that reframes the context in which such a twin was once imagined. Instead of confirming the Nemesis hypothesis, it illuminates the diversity of objects that share the Sun's larger galactic environment. None belong to it, none follow its motion, none hold the gravitational imprint that would betray ancient companionship. And in this stillness the conclusion becomes gentle rather than definitive. The Sun, though born in a crowded stellar nursery, now travels alone among neighbours whose faint light forms a quiet, shimmering backdrop. The infrared darkness holds no guardian or threat, no periodic perturber, only a population of small, cool wanderers that reshape understanding of the galaxy, while leaving the question of an ancient twin resting peacefully in the realm of what once might have been softened by the vastness of time and the limits of what present observation can reveal. Planetary motions in a restless halo begin with a recognition that the solar system, though often described as a quiet clockwork of stable orbits, resides within a galactic environment that never truly stands still. The sun moves through the Milky Way on a vast, slowly curving path, carrying with it not only the planets, but the distant halo of comets that form the Oort cloud. This halo extends so far beyond the familiar planetary region that it behaves less like a coherent part of the solar system and more like a fragile envelope shaped equally by internal gravity and external galactic forces. Even as the inner planets circle the sun with reassuring predictability, the outermost reaches drift according to influences older, larger, and less predictable than the solar system itself. A scientifically grounded fact anchors this section. The sun completes one orbit around the Milky Way approximately every few 100 million years, and during this journey it encounters regions of varying stellar density, molecular clouds, and subtle changes in the galactic tidal field. These influences exert imperceptible effects on the inner planets, but play measurable roles in the distant Oort cloud, where the sun's pull weakens and small perturbations accumulate over vast spans of time. The halo of comets does not orbit neatly in a plane like the planets. Instead, it forms a diffuse sphere shaped by the combined gravitational reach of the sun and the larger structure of the Milky Way. A lesser-known detail adds quiet richness, as the sun oscillates above and below the galactic plane, completing a vertical cycle roughly every several tens of millions of years. The strength of the galactic tide changes. When the sun moves closer to the dense midplane, the tidal influence increases slightly, altering the distribution of cometary orbits at the outer edge of the halo. This oscillation has been proposed as one of several factors that may indirectly modulate the rate at which comets fall inward, though its influence remains small and blended with numerous other forces. These oscillations do not produce strict periodicity, nor do they generate sharp patterns, but they do remind us that the solar system does not travel through a uniform environment. Yet uncertainties remain woven into the complex gravitational structure of the galaxy. The precise density of the galactic plane, the distribution of mass in the spiral arms, and the scale of local substructures all remain subjects of active study. These uncertainties translate into small ambiguities in models predicting how the galactic tide interacts with the Oort cloud. Even small errors in galactic mass distribution propagate into large uncertainties, when applied to regions so distant that comets respond to gravitational fields barely stronger than the pull of a passing star. The first soft irony arises from this fragility. The most distant members of the solar system, though bound to the sun, feel the galaxy more strongly than they feel the planets existing in a space where the solar system's identity merges with the larger gravitational environment. A second gentle irony rests in the fact that although the planets orbit with near-perfect stability, the halo surrounding them behaves almost like a weather system, at the edge of the solar system, slow, diffuse, and endlessly shaped by distant forces. A third emerges in the contrast between perception and reality. While the solar system is often depicted as a neat, self-contained structure, its outer boundary is not fixed, but permeable, drifting, and constantly rewritten by the galaxy. Stars passing within a few light-years of the sun add another layer of complexity. Although these encounters are rare, occurring roughly every few 100,000 years, they can impart small but lasting gravitational nudges to the outer cloud. Some stars pass close enough that their influence becomes detectable in simulations, shifting the orbits of thousands of comets at once subtly redistributing the outer halo. The most notable example in recent astronomy is Schultz's star, which passed within a light year of the Sun roughly 70,000 years ago. Though the encounter did not disturb the planetary region, its gravitational influence likely touched the very outer edge of the Oort cloud, illustrating how even dim, low-mass stars shape the solar system in ways invisible to the inner worlds. A gentle uncertainty lingers here as well. Most past stellar encounters cannot be traced, because the motions of stars become increasingly uncertain when projected backward more than a few million years. This prevents reconstruction of the solar system's full encounter history, leaving open the possibility that ancient passages closer, brighter, or more influential once shaped the distant halo in ways the modern distribution only hints at. As the Sun moves through the galaxy, it also traverses regions of differing interstellar gas density. Though the heliosphere protects the planets from most external influences, its boundary expands and contracts depending on the surrounding medium. When the Sun enters denser regions, the heliosphere compresses, shifting the conditions under which charged particles and cosmic rays interact with the solar wind. While these variations have little effect on the planets, they contribute subtly to the dynamics of dust and charged particles near the solar system's edge. In the distant halo, where forces are balanced at the threshold of solar gravity, such small changes may alter the behavior of fine material suspended between the inner and outer domains. Meanwhile, the planets continue their steady motions, unaware of the faint gravitational currents shaping the halo that surrounds them. Jupiter's mass still governs the architecture of the inner cometary reservoirs. Saturn, Uranus, and Neptune maintain their roles in guiding the orbits of scattered icy bodies in the Kuiper belt. But beyond these familiar boundaries, the Oort cloud behaves almost like an independent structure, loosely bound, softly shaped, drifting through galactic tides in patterns that reflect the Sun's larger journey. The interplay between planetary stability and halo drift creates a subtle paradox. The solar system appears self-contained, governed by the predictable mechanics of Newton's laws, yet its outer layers are continually reshaped by galactic influences, blurring the line between solar and galactic domains. A soft, modern analogy captures this relationship. The solar system resembles a lantern carried through a vast night landscape. Its interior remains bright and orderly, but its halo flickers in response to passing breezes, distant movements, and the unseen contours of the darkness around it. This analogy illustrates the way the Sun's motion influences the cloud without altering the stability of the inner planets. The concept of a lost solar companion enters this picture indirectly. If a companion star once orbited the Sun at great distance, its presence would have shaped the early distribution of the halo. But the galaxy itself, through its tidal field and passing encounters, can mimic many of the long-term effects that a companion might produce. This overlap complicates attempts to identify distinctive features in the Oort cloud that could reveal past companionship. The halo's present form carries the imprint of billions of years of galactic motion, making it difficult to determine which features arise from early solar history and which from the Sun's long journey through the Milky Way. Yet the absence of necessity does not eliminate possibility. The early solar system formed in a dense cluster where interactions among stars were frequent. In such an environment, loosely bound companions could easily separate. If the Sun once had a distant twin, its influence on the halo may have been limited by the brief period during which they remained gravitationally linked. Once separated, the companion's long-term influence would vanish, leaving only the galaxy to guide the cloud's evolution. The present distribution of comets thus reflects a complex interplay of early chaos, followed by long epochs of gentle, persistent galactic shaping. In this restless halo, planetary motions remain predictable, but the space beyond them drifts in response to forces that operate far beyond the Sun's immediate influence. This combination of stability and subtle change defines the outer solar system, a place where history unfolds at the intersection of solar gravity and galactic motion, where the possibility of a long-faded companion remains only one thread among many. And through this expansive, slow-moving environment, the Sun continues its quiet orbit around the galaxy, carrying a halo that remembers fragments of its earliest past while constantly reshaping itself under the soft pull of the Milky Way. Uncertainties at the galactic edge begin with the recognition that the solar system, though seemingly complete within its familiar planetary boundaries, extends into a realm where the Sun's gravitational authority weakens into a soft, permeable horizon. At these distances, tens of thousands of astronomical units from the Sun, the forces that shape the motions of small bodies no longer arise solely from solar gravity, but from the layered, shifting structure of the Milky Way itself. This galactic edge is not a physical boundary, but an ever-changing gradient where the solar system blends into interstellar space, a place defined as much by uncertainty as by measurable patterns. A scientifically grounded fact anchors this section. The Sun's gravitational dominance extends only so far as its Hill sphere, a region whose radius varies as the Sun moves through the galaxy, but is conventionally estimated to be less than 2 light-years. Beyond this region, the Sun cannot retain long-term gravitational control over orbiting objects. Within it, the outermost members of the Oort cloud remain loosely bound. These bodies live in a delicate balance between the Sun's diminishing pull and the gravitational tides imposed by the Milky Way. Their orbits reflect this tension, following paths shaped not only by early solar history, but by billions of years of galactic influence. A lesser-known detail adds quiet depth. The galactic tide itself differs depending on direction. Along the plane of the galaxy, gravitational forces compress and stretch orbits in a soft horizontal rhythm. Perpendicular to the plane, vertical oscillations nudge cometary paths upward or downward over immense timescales. These directional differences create a subtle asymmetry in the distribution of the Oort cloud, making it slightly denser in some regions than in others, a feature predicted by theory but impossible to observe directly. This hidden structure remains one of the solar system's most elusive architectural elements, inferred from models and the behavior of long-period comets rather than from any direct detection. Yet uncertainties hover around every aspect of this distant realm. The density of the Milky Way's dark matter, halo the mass distribution of the local stellar neighborhood, and the precise shape of the galactic gravitational potential all remain partially unknown. These uncertainties translate into imprecision in modeling how the Oort cloud evolves over billions of years. Small differences in galactic parameters lead to large variations in predicted cometary distributions. The shape, size, and even the population of the Oort cloud carry margins so broad that they resist definitive characterization. Here the first soft irony emerges. Although the solar system's distant boundary is shaped over billions of years, the galaxy's structure on which this shaping depends remains only partially understood. A second gentle irony rests in the fact that the outermost solar system, often imagined as a static reservoir, is in reality a dynamic region continually responding to galactic variations too slow for humans to perceive. A third lies in the asymmetry between what can be known of the inner and outer solar system. While planetary orbits are measured with exquisite precision, the orbits of trillions of distant icy bodies remain unknown, even though they form the majority of the solar system's spatial extent. The Sun's journey through different galactic environments further complicates the story. As it orbits the Milky Way, it encounters regions of varying stellar density passing near clusters, local associations, and individual stars. Each encounter, however distant, contributes gently to the evolution of the Oort cloud. Some encounters may have stripped away entire regions of the outer halo. Others may have added new bodies captured during close approaches. Though direct evidence for such exchanges remains beyond reach, simulations show that interactions of this type are inevitable. They also demonstrate how little of the solar system's distant history can be reconstructed with certainty. The Oort cloud today is the cumulative product of influences too numerous and dispersed to fully map. Passing molecular clouds, vast aggregations of gas and dust, add another layer of uncertainty. When the Sun moves near these giant structures, their collective gravity can alter the outermost orbits of comets. Such interactions, though gentle, accumulate over time, contributing to large-scale distortions in the Oort cloud. But because the motions of ancient molecular clouds cannot be traced backward with precision, their roles remain speculative, their gravitational fingerprints blurred by time. The lack of detailed knowledge about these past encounters introduces another scientific mystery: whether features of the Oort cloud that appear today as irregularities might once have been shaped by a transient passage through a denser or more turbulent region of the galaxy. Amid these uncertainties, the Sun also completes its vertical oscillation through the galactic plane, rising above it and sinking below it in cycles that unfold over tens of millions of years. This motion subtly alters the gravitational field experienced by the solar system. When the Sun is nearer the galactic midplane where stars, dust and gas concentrate, the galactic tide grows slightly stronger and cometary orbits in the outer cloud shift accordingly. When the Sun moves farther from the plane, the tide weakens. These oscillations do not impose strict periodicity, but introduce long-term gravitational variability that reshapes the distant halo in ways that resist simple modelling. A gentle modern analogy helps clarify the situation. The solar system behaves like a ship sailing across a deep ocean, whose currents and subtle swells influence objects floating in the water hundreds of meters away from the hull. The ship's immediate surroundings remain stable, but the distant flotsam drifts according to forces that the ship's crew cannot see. In this analogy, the inner planets are the stable deck of the ship, while the Oort cloud represents the scattered debris responding to both the ship's movement and the larger ocean's dynamics. Into this uncertain environment enters the question of the Sun's lost companion. If such a companion once existed at great distance, its gravitational influence would have been woven into the early structure of the Oort cloud. But as the Sun drifted through the galaxy, leaving its birth cluster, passing through regions of varying density, experiencing encounters with other stars, any early signatures of companionship would have been gradually overwritten. Galactic tides, stellar encounters, and molecular cloud passages would all have contributed to erasing or reshaping these features. As a result, even if the Sun did once have a wide separation companion, the present distribution of distant comets may no longer carry a trace of that relationship. This possibility illustrates another soft irony. The galaxy's tendency to erase the past means that some aspects of the solar system's early history may remain unknowable, not through lack of effort, but through the natural evolution of gravitational systems over immense spans of time. Yet not all mysteries fade completely. Certain long-term features, such as the potential flattening of the inner Oort cloud or the slight anisotropy in comet arrival directions, remain topics of study precisely because they might reflect ancient influences. But these features can often be explained by multiple mechanisms, making them ambiguous indicators of specific events. The edge of the solar system, shaped by both internal and external forces, Thus becomes a landscape where evidence is plentiful but interpretation remains delicate. This interplay of clarity and obscurity defines the galactic edge, a region where the sun's influence wanes, where the galaxy's vast gravity takes precedence, and where the search for signs of past companionship becomes a quiet exercise in acknowledging uncertainty. Through this expanse, the solar system continues its journey around the Milky Way, carrying with it a halo that remembers much, yet reveals little, shaped by forces that operate at the boundary between the sun's personal history and the galaxy's immense indifferent drift. The fading of a hypothesis begins not with a dramatic refutation, but with the gradual accumulation of evidence that gently, steadily shifts the balance of understanding. Ideas in science rarely vanish all at once. Instead, they soften at the edges, lose their explanatory necessity, and eventually become historical footnotes that once guided curiosity in useful directions. The Nemesis hypothesis followed this quiet trajectory. Born from an attempt to align geological periodicities with celestial mechanics, it drew attention for its interdisciplinary boldness. It suggested that a distant companion, star-dark, faint and orbiting at immense distance, might periodically disturb the Oort cloud and send waves of comets toward Earth, shaping cycles of extinction. But as new data arrived, the foundation beneath this idea thinned not through contradiction but through refinement. A scientifically grounded fact anchors this section. Successive improvements in both paleontological datasets and astronomical surveys steadily weakened the case for a periodic comet-driven extinction mechanism. Modern stratigraphy, enhanced fossil sampling, and more robust statistical methods reveal extinction events that occur neither with rhythmic regularity nor with synchronized environmental markers that would indicate a single recurring cause. Meanwhile, infrared sky surveys, particularly those capable of detecting cool, dim substellar bodies, found no companion of the mass and distance required to meaningfully perturb the Oort cloud on cycles of tens of millions of years. A lesser-known detail brings quiet nuance to this transition. Early models of periodicity relied on fossil datasets, dominated by marine invertebrates, with large sampling gaps that created the illusion of regular patterns. Later analyses incorporating microfossils, terrestrial plants and vertebrates revealed far more variable extinction tempos, stretching or compressing events beyond the predicted cycles. This shift did not negate the original observations, it contextualized them, revealing the influence of sampling bias, preservational gaps and uneven global coverage. Through this refined lens, geological rhythms appeared less like cosmic metronomes and more like overlapping environmental fluctuations shaped by Earth's internal dynamics. Yet uncertainties linger even as the hypothesis fades. The structure of the Oort cloud remains inferred rather than observed. Its population density and formation history remain only partially constrained. Without direct detection of its trillions of icy bodies, reconstructing its past perturbations demands reliance on models sensitive to initial assumptions. Similarly, the Sun's early stellar environment cannot be reconstructed with precision. Its birth cluster dissolved long ago, scattering siblings across the galaxy. Whether a wide companion once accompanied the Sun before drifting away remains an open question, though this possibility belongs to a narrative distinct from the Nemesis mechanism. And so, the first soft irony arises while the Sun's solitude today appears certain. The question of its earliest companionship remains one of the least accessible chapters of solar history. A second gentle irony flows from the hypothesis itself. Although Nemesis likely does not exist, the effort to find it dramatically expanded knowledge of the solar neighborhood, revealing a rich population of nearby brown dwarfs and faint stars that had gone unnoticed for decades. A third lies in the way the hypothesis proposed as a dramatic explanation for mass extinctions ultimately helped strengthen the understanding that most extinction events arise from earthbound processes, underscoring the planet's own capacity to reshape its biosphere. As the Nemesis hypothesis faded from scientific discourse, the search for solar companions continued in quieter, more nuanced forms. Instead of seeking a catastrophe-inducing object, astronomers turned to studying the Sun's possible origin in a wide binary system, a formation topology supported by star formation statistics. Most Sun-like stars, after all, are born with companions. Many of these wide binaries are fragile, prone to disruption during the early chaotic phase of cluster dispersal. A companion drifting thousands of astronomical units away would have been especially susceptible to separation. Thus, the possibility that the Sun once had a twin that later drifted off remains conceivable even if no such twin exists today. This distinction between current absence and ancient companionship has become central in modern discussions. Still, uncertainties surround the mechanisms of binary disruption. Models show that stellar encounters within dense birth clusters can gently dissolve wide binaries within a few million years. But the exact density of the Sun's natal environment remains unknown, as does the cluster's lifespan and membership. Without these parameters simulating whether a companion could have existed long enough to leave an imprint on the early Oort cloud becomes speculative. And so even as Nemesis fades as an active hypothesis, the broader question of the Sun's natal history persists. The fading of Nemesis parallels advances in understanding the galaxy's gravitational environment. Researchers now recognize that the Milky Way's tides passing stars and molecular cloud encounters shape the Oort cloud in ways once attributed exclusively to a companion star. This recognition softens earlier interpretations of clustering within long-period comet orbits. Such patterns can arise naturally from galactic structure rather than from an internal perturber. Over time, models incorporating realistic galactic influences revealed a tapestry of forces far more intricate than early Nemesis models allowed. This complexity forms the backdrop against which the hypothesis receded, not through contradiction, but through enriched explanation. A gentle modern analogy helps frame this shift. Nemesis was once imagined as a single hand stirring a distant pool of icy bodies, but modern understanding reveals a pool stirred by the larger currents of the galaxy itself, leaving little need to posit an additional unseen hand. Infrared surveys provided the final constraints. WISE, with its ability to detect objects at temperatures only a few hundred Kelvin above absolute zero, effectively ruled out any brown dwarf or low-mass star within the distance range required for Nemesis-like behavior. Gaia's astrometric precision further limited the parameter space, showing no co-moving companion across millions of catalogued stars. Under these constraints, the hypothesis had little room left to survive. Yet its fading leaves behind a legacy one of exploration and refined understanding. It stimulated improvements in survey depth detection algorithms, statistical modeling, and interdisciplinary collaboration. It broadened the narrative of extinction research, prompting geologists and astronomers to examine shared questions across scales that once seemed too disparate to connect. And it illuminated the delicate balance between Earth's internal rhythms and the galaxy's gentle gravitational background. In this quiet end, the hypothesis dissolves without drama. The Oort cloud remains influenced by tides and stellar passages. Mass extinctions remain driven largely by Earth's own geological dynamics. The Sun continues through the galaxy without a partner bound to it by gravity. What remains is a softened possibility not of a dark star lurking in the present darkness, but of an ancient twin that may have drifted away before memory or solar architecture could record its presence. And so, Nemesis fades not into dismissal, but into the wider tapestry of early solar history, a gentle reminder that scientific ideas evolve not only through correction, but through the steady expansion of knowledge that reveals broader, quieter truths. A solitary star beneath moving dust takes shape as the sun enters the long middle stretch of its life, shining with the steadiness that belies the turbulence of its earliest beginnings. The distant possibility of a twin once envisioned as a hidden presence, influencing cycles of extinction, or shaping the farthest reaches of the Oort cloud, has faded into a gentle question rather than an active hypothesis. What remains is the reality of a single star travelling through a galaxy filled with drifting molecular clouds passing stars and faint substellar wanderers, all moving according to rhythms older than the solar system itself. Against this vast backdrop, the sun stands alone, not dramatically but quietly, its isolation no longer a puzzle to be solved but a natural outcome of galactic evolution. A scientifically grounded fact anchors this section. The sun today has no gravitationally bound companion within the limits measured by modern surveys, and its heliosphere moves through the interstellar medium shaped solely by its own winds and motion. Infrared and astrometric data show no co-moving star-brown dwarf or substellar object following the sun's galactic trajectory. Instead, the solar system drifts independently its position, defined by the balance between solar gravity and the galaxy's broader gravitational field. A lesser-known detail adds quiet texture to this solitary image. The sun emits a constant outflow of charged particles that form the heliosphere, a vast teardrop-shaped bubble, stretching billions of kilometers into space. This bubble interacts with the local interstellar medium, creating boundaries where magnetic fields meet and particles mix. These boundaries shift as the sun moves through regions of varying density, revealing subtle changes in the interstellar environment that would be more complex to interpret had a companion star also exerted influence. The heliosphere's shape therefore acts as a silent tracer of the sun's solitary motion through the galaxy. Yet uncertainties drift through this space like the dust grains illuminated by the sun's distant light. The structure of the interstellar medium remains patchy and incompletely mapped, with clouds, voids and filamentary structures distributed in ways that defy simple characterization. The sun is currently travelling through a region known as the local interstellar cloud, a small pocket of warm diffuse gas whose boundaries and density remain only partially known. As the solar system moves forward, it will eventually enter new environments that may subtly reshape the heliosphere's contours. These future transitions highlight a gentle mystery. The sun's path through the galaxy intersects structures too faint and dynamic to predict far into the future. The first soft irony arises from this interplay. The sun's current solitude makes its journey through the galaxy easier to trace, even as the uncertainties of the galactic environment obscure the fine details of that path. A second gentle irony lies in the way the sun's isolation contrasts with the early likelihood of companionship, an echo of the many stars that form in pairs, only to lose their partners as they drift through their birth clusters. A third rests in the fact that while the planets orbit the sun with precise regularity, the solar system's place within the galaxy evolves according to forces far less predictable, shaped by structures that cannot be seen with visible light. In this drifting motion, the solar system encounters streams of interstellar dust, tiny grains that flow through the heliosphere and settle into trajectories influenced by solar gravity and radiation pressure. These grains, remnants of ancient stellar processes, add a slow, steady rain of material that the sun collects as it moves. The dust carries chemical signatures of supernova dying stars and molecular clouds long dispersed. Its presence highlights a subtle scientific truth: even if the Sun is solitary, it is never isolated. It interacts continuously with the galaxy, gathering particles older than the solar system and releasing charged winds that merge into the broader interstellar medium. Meanwhile, the planets maintain their steady orbits, largely unaffected by these distant influences. Mercury, Venus, Earth and Mars continue their inner dances. Jupiter and Saturn shepherd smaller bodies in the asteroid and Kuiper belts. Uranus and Neptune remain on the outer edges of the planetary realm, distant yet firmly tied to the Sun's gravity. Beyond them, the scattered disk and the sparse outer Kuiper belt fade into the darkness, where Oort cloud objects begin their long, slow drift. In this architecture, the absence of a companion star simplifies the long-term evolution of planetary orbits. There are no competing gravitational fields to alter trajectories, no distant mass to introduce irregularities. Planetary motion reflects the Sun's central dominance, shaped only by mutual perturbations, and the slow adjustments dictated by tides raised within the Sun itself. If a companion had existed in the distant past, its departure left no lingering instability. Instead, the solar system today appears as a clean, stable configuration, a quiet outcome rather than a dramatic one. And yet the possibility of a lost twin lingers softly in the background, not as a driver of current dynamics, but as a feature of the Sun's earliest history that remains partially inaccessible. If the Sun once formed as part of a wide binary system, its partner may have drifted away billions of years ago, joining the general population of field stars. Today, that star, if it exists at all, would be indistinguishable from the countless others moving through the galaxy, its shared origin impossible to trace without highly specific chemical signatures or precise knowledge of the Sun's birth cluster data that lie beyond modern reach. This gentle uncertainty highlights another quiet mystery. The galaxy, through its slow, gravitational reshaping, erases the signatures of ancient relationships, leaving the present configuration clean but detached from its earliest context. The solar system's solitary nature today offers clarity even as it conceals its deeper past. A soft modern analogy captures this dynamic. The Sun is like a traveller who has walked so far from childhood companions that even the path back has dissolved, leaving only the memory that companionship was once possible. The surrounding galaxy moves with equal indifference, its stars drifting in long, slow arcs, each following its own history shaped by birth environments long since forgotten. Yet even in solitude, the Sun remains part of a larger pattern. Dust clouds shift around it. Cosmic rays flow through its heliosphere. Distant stars exert faint cumulative influences that shape the cloud of ancient comets at the edge of gravitational reach. The solar system's boundary is not a wall, but a region of subtle negotiation where internal and external forces meet. In such a space, the Sun's isolation becomes not a conclusion, but a condition, one that reveals the serenity of its current state, while leaving open the lingering possibility that its earliest origins included companions now lost to the galaxy's slow dispersal. Through all this, the Sun continues its quiet orbit around the Milky Way, a solitary star beneath drifting interstellar dust, carrying a planetary system that long ago settled into stable motion. The question of companionship fades into gentleness, replaced by the recognition that the solar system's beauty arises not from what it lacks, but from the quiet interplay of forces that shape it across time. The rhythm begins to soften now, as if the long arc of the solar system's history slowly dissolves into a broader stillness. The Sun continues its quiet journey through the Milky Way, and the spaces around it widen into calm, drifting fields of dust where light thins gently into the interstellar dark. Nothing here moves quickly. Even the smallest grains stirred by distant magnetic fields or the faint push of radiation pressure drift with the unhurried grace of something that has never known urgency. The story of the Sun's possible twin has faded into this calm as well, not erased, not dismissed, simply settled into the soft understanding that some questions lose their sharpness as time stretches. Evidence disperses, gravitational signatures blur, and the galaxy itself slowly reworks the boundaries of every system it holds. What remains is the quiet certainty that the Sun moves alone now, carrying a halo of ancient fragments, and the steady warmth that has illuminated the planets for billions of years. In this gentle, quiet uncertainties no longer seek resolution. They drift like the dust at the edge of the heliosphere, suspended between what can be known and what has already slipped into deep time. The distant comets remain at their stations in the Oort, cloud barely touched by the Sun's faint pull, their orbits stretching far into galactic space, where tides shape their paths with a softness that mirrors the slow breathing of the Milky Way. If any memory of early companionship exists among them, it lies beyond the reach of models and measurements, carried only as a structural whisper within a vast unseen sphere. Yet even here the mystery brings no restlessness. It settles instead into the calm that follows long exploration, the quiet contentment of understanding that not all stories end with answers, and that some of the universe's oldest truths lie in its silences. As the Sun continues its drift through the local interstellar cloud, the heliosphere glows faintly at its boundaries, a protective envelope that expands and contracts according to the gentle changes in the medium around it. This motion introduces no drama, only gradual adjustments, like a subtle shift in temperature felt by someone resting under open sky. The planets move in their familiar paths, unchanged by questions that once rose from Earth about distant companions or hidden influences. Their orbits remain steady, shaped by the Sun alone, carrying the quiet history of a system that found stability not through cosmic partnership, but through the quiet balance of gravity, motion, and time. In this final stillness, the galaxy becomes a vast, dim landscape stretching in every direction, filled with drifting stars and cool substellar wanderers. None of them move with the Sun's specific rhythm. None share its trajectory through the spiral arm. None carry the signature of a bound companion. And yet the absence of such a twin does not diminish the sense of belonging within the Milky Way's slow architecture. Instead, it reveals a different kind of companionship, the collective drift of countless stars following their own long, quiet orbits across the galactic disk. The Sun is one among them, solitary but never alone. The long journey of this narrative softens here into a kind of geological rest, where motion slows into silence and inquiry settles into calm. The ancient question of the Sun's dark twin fades into the wider sweep of cosmic history, replaced by the awareness that the universe carries more mysteries than any single story can contain. And as the solar system continues its drift through the galactic night, the quiet glow of the Sun lights its path with a steadiness that asks nothing and promises only the continuation of slow, patient time.